Assalamu alaikum. All right. I welcome you to our second lecture in this model. And before we start our second lecture, let us make a recap of what we discussed in our last lecture. In the first lecture, we talked about the atomic structures, where we said that an atom consists of three subparticles. Talked about the electrons, negatively charged, protons, positively charged, and the neutrons, chargeless. We said that the protons and neutrons are glued together within the nucleus, whereas the electrons orbit around the nucleus. We talk about the presentation of or rather notation of nuclides, how it's being presented with respect to mass and the atomic number, where we said that the superscript will be the mass number, the subscript will be the atomic number. Then we talked about the classification of nuclides. We talked about the isotope, isobars, isoton, and isomers. Now today, we are going to take a voyage to talk about the electron orbitals and principal quantums. Now, as we had said that from the knowledge of Bohr postulated the electron to exist in some set of energy level, or some set of orbital called the energy levels. Now, the understanding of the electrons orbitals and energy level is of obvious importance, as it forms the baseline for the understanding of the atomic behavior of an element. Now that the closer the energy level to the nuclear, the stronger the force of attraction between the nuclear and the electrons within that energy levels. Now, the number of energy levels extend from normally it extends out from the molecule, from the nucleus. And the number of electrons those shells occupy those shells accommodate different amount of or different number of electrons, depending on which quantum number the energy level is. Now, the number of electrons occupied by each and every quantum increase from the nuclear, as we have the K shell, the L shell, the M shell, we have the N shell, we have the O shell, and the P shell. Now, the number which these nuclear orbitals contain increase from the nuclear as they move down. Now, and then the number of the electrons that each and every principal quantum number can accommodate can be obtained using this kind of formula, where it is 2n squared, where n is the principal quantum number. Like, for instance, we have the K shell. K shell is the innermost shell. Then we have the L shell, which is the second innermost. Then we have the M shell, we have the N shell, we have the O shell, we have the P shell. Now, how these shells accommodate electrons is informed by this formula, because if we take an example of K shell, which is having a principal quantum number of 1, and then we substitute that 1 into this formula, we are going to have 2 electrons, because we have 1 square multiplied by 2 will give us 2 electrons. Now, if we take the principal quantum number 2, that is L shell. L shell is having quantum number of 2. Now, if we substitute the 2 here, clearly we are going to have 8 electrons in the second energy level. Then when we come to the third energy level, we are going to have 18 electrons, and meaning it keeps on increasing from K to P. As you move away from the nuclear, the number of electrons that are being obtained by each and every principal quantum number increases. But the formula that informs that increment is this formula here. This is the formula that informs the increment. Now, As these elements orbit around the nucleus, they are held by some strong force called binding energy. Now, binding energy is nothing other than the energy required to release an electron from an atom itself. It is fundamental, and fundamentally it depends in some two obvious factors. And the first factor is the proximity to the electron. Our proximity is that quantum principal number to the electron, to the nucleus. If it is closer to the nucleus, it means that the force of attraction, the binding energy is going to be very strong as compared to a quantum principle that is far off the energy level. So we will realize, you will appreciate the fact that K is having high energy, high binding energy as compared to L shell, and L shell is having high binding energy as compared to M shell. Now we have the second property that influence the binding energy. The second property is the number of protons in the nucleus. Now the number of the protons in the nucleus, the stronger the force of attraction of the electrons to the nucleus. Because when the number of electrons increase within the nucleus, then it means that the positivity increases, and therefore the nucleus becomes more positive. And if the nucleus is more positive, then the force of attraction, the electromagnetic force, which is called the nuclear energy, is also strong. As you understand, if you increase the strength of the magnet, the force of attraction becomes very fast, as compared to when you have a weak magnet. That is really what happens here. Now clearly this shows that the K shell energy is greater than the L shell binding energy. So it means as we move again away from the nucleus, the binding energy decreases. And this decrease in binding energy informs what we are going to talk about, formation of characteristic X-rays, as we are going to discuss both characteristic and brainstorm kind of X-rays as we move of course. Now, the change in the energy level is what brings in the characteristics X-ray. And it will be important to note that the K shell is having stronger binding energy because it is closer. One, it is closer to the nuclear. And again, if the number of protons increases within the nucleus, then the binding energy of that element is also going to be high. And we must acknowledge the fact also that the binding energy decreases as we move away from the nucleus. Now, we have electron orbitals, as was discovered by Bohr. Now, as we said that electron orbitals are these are specific paths that electrons fall or electrons orbit. But now Bohr did not just stop at identifying electrons to exist in orbitals, but it told us that the electron orbitals are a 3D configuration where they shows the region where there is likelihood of finding an electron. Now within this 3D space, we always have 4 classes, and the 4 classes, one of them is the p orbital. I mean the s orbital. We start with the s orbital, then we move to the p orbital. Then from p orbital, then we have the d orbital, and the 4th will be f orbital. Now the s orbital is the first orbital. This orbital normally holds only one electron pair, and an electron pair means that they move in spin of 2 electrons opposing each other. Remember, they oppose each other. One goes up and one goes down. There is one pair. So s orbital has only one pair electron, which means that the total number of electrons that can be accommodated by our s orbital here is only 2 electrons. Then we have our p orbital. P orbital can accommodate 3 pair electrons. Now, if it can accommodate 3 pair electrons, then it means that the total number of electrons that can be held or that can be accommodated by the p orbital will be 6 electrons. 2 pair or 2 times 3 gives us 6 electrons. Then we have d orbital. In the d orbital, D can accommodate 5 pair electrons, and these 5 pair electrons fundamentally informs that D can accommodate 10 electrons, a maximum of 10 electrons. It cannot go beyond that. Then we have F orbitals as the last orbital. Now, F orbital can accommodate 7 pair electrons. And if it can accommodate 7 pair electrons, then it means that it can hold a maximum of 14 electrons. So it is important to understand the nomenclature of the orbitals. You see that we have S orbital that can accommodate only a maximum of 2 electrons. We have p orbitals that can accommodate a maximum of 6 electrons. Then we have d orbitals that can accommodate a maximum of 10 electrons. Then we have F orbital that can accommodate a maximum of 14 electrons. This nomenclature is equivalently important because it helps us in assigning electrons or putting electrons into the configuration. Now you can maybe take an example of oxygen 16. Now oxygen 16 is having atomic number of 6. And if it has atomic number of 6, this is a stable, it's not an isotope yet. So this one clearly shows us that it has electrons of 8 electrons. And if it has 8 electrons, then how do we feel it? How do we feel it in the orbitals? Like we have the K shell. K shell we say that can only accommodate 2 electrons, being the first quantum principle. Can only accommodate 1 pair, which is 2 electrons. So the case of carbon 16, not carbon 16, but oxygen 16, we have 8 electrons. Now, how are we going to present these 8 electrons? Here we use the diagonal rule, where K orbital will accommodate only 2 electrons. The remaining electrons will be 6. Now, the 6 electrons, first 2 electrons will be accommodated by L shell, 2 S shell in the L principal quantum here. So these 2 will accommodate 2 electrons. This 2s will accommodate 2 electrons, leaving us with 8 electrons. Leaving us with 4 electrons. Now, if we are remaining with 8 electrons, 2 has been accommodated here, 2 has been accommodated here, 4 now is accommodated. So we are remaining with 4 electrons. The 4 electrons will be accommodated in the P. Now that we say that the P orbital can accommodate a maximum of 6 electrons, and we are having the remnant of the electrons here is 4. So those 4 can be accommodated here. So it means that we have this diagonal shows the diagonal line determines how we feel the orbitals. So far we have looked at the atom to exist in subatomic particles, that is proton, neutrons, and electrons, which forms the classical model and with respect to the Bohr and Rutherford classification. But now when we start looking at the atoms in terms of how they are being built, how they're periodic table, and how they're being, then now we move deeper into the modern physics or quantum physics. And now it makes us be curious enough and know that atoms are still subdivided into protons and neutrons into smaller packets of quantum masses and energy. And this we will be able to discuss when we start discussing about the forces down the course. Now, in our next class, we are going to discuss the atomic particles. What are these particles, the atomic particles? We are going to understand how particles is being divided. How does a particle being divided? And we'll see how the forces of attraction, the types of forces that exist within the particle in our next class. Otherwise, thank you very much for your time and see you in the next class.